This is Chapter 11, Section 8. This is the last section on buffers. A buffer is a solution that resists changes in pH when you add acids or bases to it. It's able to do this because it contains components of acid and base in small amounts, which resist the addition of hydroxide or hydronium ions. In this section, we're going to learn about the role of buffers in maintaining the pH of a solution, as well as how to calculate the pH of a buffer. Remember that when you add an acid or a base to pure water, the pH changes drastically. Even a small amount of acid is enough to change the pH of neutral water from 7 down to something like a 4. A small amount of base will cause the pH to rise to something like 10 or 11. In a buffer solution, however, the pH is maintained approximately constant. So if the pH starts at 7 and you add a little bit of acid to it, the pH is only going to decrease a little bit to 6.9 or so. If you add a small amount of base, it'll only go up a little bit, maybe to 7.1. It doesn't maintain it perfectly constant, but it keeps it within a certain range for a given amount of acid and base that you can add to it. So buffers maintain an approximately constant pH by resisting the addition of acids or bases. But no buffer is infinite. Every buffer has a maximum capacity for the amount of acid or base that it can neutralize. In your body, there are natural buffers that are responsible for absorbing excess hydronium or hydroxide from the foods that you eat or that are produced as a result of cellular and metabolic processes. For instance, your blood has a pH of close to 7.4 maintained by a natural buffer, and this is necessary for the proper functioning of cells. Every buffer solution is made from a weak acid-base conjugate pair. This means either a weak acid and its conjugate base, or a weak base and its conjugate acid. Really, these are the same thing because you need both components to be weak so that both of them will be present in equilibrium in the buffer. In this example, you have acetic acid, HC2H3O2, and the acetate ion, C2H3O2-. If you take the formula for acetic acid and you remove the hydrogen ion in front, then you end up with the acetate ion. That's how you know that this is a conjugate pair. If you try and use a strong acid or a strong base in a buffer solution, it'll fully dissociate and the conjugate won't be powerful enough to provide any neutralizing power to the buffer. You may remember that if you add a weak acid or a weak base to water or to a solution, it will dissociate and form an equilibrium with its conjugate. However, these equilibrium generally lie very far to one side. So if you take acetic acid and you dissolve it in water, you're not going to end up with very much acetate ion at all, which means it's not going to behave as a buffer very well. To fix this, you need to add some additional conjugate, in this case a salt of the conjugate base, in order to make the concentrations of the two roughly equal at equilibrium. So let's see this example in a little more detail. You can take acetic acid and you can dissolve it into water, and you'll end up with a large amount of the neutral, undissociated form of the acid, and a very small amount of the conjugate base, the acetate ion. This won't work as a buffer because there's not enough of the acetate ion to really resist or neutralize the addition of acid. To make it a buffer, we have to increase the amount of this conjugate base. However, the conjugate base here is an ion, and this is often the case. We can't just add ions to solution because you can't keep ions in a bottle. In order to get ions into a usable form, you have to neutralize them so that they can form a solid. So instead of just saying that we add the conjugate base, we make a salt of the conjugate base, or we use a salt of the conjugate base, such as sodium acetate. We want to use a salt that's highly soluble, and so the conjugate base ion is generally combined with one of the first group metals, like sodium, potassium, or lithium, and this forms a salt which completely dissociates in solution. So we can add enough sodium acetate to the solution to produce a bunch of acetate ions that we need. We'll also be introducing some sodium ions, but those don't affect the pH or anything else. So by combining similar amounts of acetic acid and the acetate salt, in this case sodium acetate, we now have a buffer. We have relatively large amounts and roughly equal amounts of acetic acid and its conjugate base, the acetate ions. The acetic acid in the solution is going to neutralize the addition of any base, which will prevent the hydroxide ion concentration from increasing too much. The acetate ions, on the other hand, will neutralize any additional acid, which will prevent the hydronium concentration from increasing too much. If we think about this, a small amount of base is going to be added, and it's going to produce some hydroxide ions. Those hydroxide ions are going to rapidly interact with an acetic acid molecule, taking a proton from it and producing water. This is going to leave behind the acetate ion. However, the acetate ion is already present in solution. It's already a primary component of the buffer. So even though the addition of a base initially served to increase the hydroxide ion concentration, those ions were quickly absorbed and neutralized into water, leaving behind a much less strong base, the acetate ion. In fact, all that we did was use up a little bit of the acetic acid and generate a little bit more of the acetate ion. So we disturbed the balance between the two components of the buffer, but this only changes the pH a very little bit. Whereas if we allowed the hydroxide ions to be introduced into the solution without forming water from them, that would change the pH a great deal. On the other side, if we take a small amount of acid and add it to the base, this is going to tend to increase the hydronium concentration initially, but these hydronium molecules are quickly going to interact with an acetate ion. They're going to donate a proton to the acetate, which is going to reform acetic acid and leave behind, again, a neutral water molecule. So instead of hydronium increasing, we're just adding a little bit more acetic acid at the expense of some of the acetate ion. In other words, we're disturbing the balance in the other direction. We're creating more acetic acid by using up some of the acetate. So again, it disturbs the balance between the two components of the buffer, but only a little bit, and this only changes the pH a small amount. The initial buffer described here had equal concentrations of acetic acid and the acetate ion, as you can see, because the bars here representing the concentrations started off at the same level. When we added a little bit of acid, it tipped the balance more towards the acid side, which caused the pH to decrease, but only by a little bit. And when we added more base, it tipped the balance towards the base side, which caused the pH to increase, but again, only a very little bit. As long as you have both components in solution, the pH is maintained within a small range. However, this also shows you why buffers have a certain capacity. If we add enough acid to completely use up all of the conjugate base, then we're only going to have acid left in the solution. The pH is going to drop rapidly. If we add enough base to use up all of the acid, then there'll be no more acid left, and the base will cause the pH to rise rapidly. If we want to be able to calculate the pH of a buffer, we need to know what acid-base components we're working with and what the relative ratio between them is. The way this works is through the equilibrium expression. We can take the dissociation of a weak acid and write down the equation for this. The acid donates a proton to water, creating hydronium and leaving behind the conjugate base. The equilibrium expression for this is the concentration of the hydronium multiplied by the concentration of the conjugate base divided by the concentration of the acid. This has all the components we need. As long as we're able to identify the acid and look up the Ka value, then we can use the relative ratio of the amount of base and the amount of acid to determine the hydronium concentration, which will then be able to give us the pH. So we can take this equilibrium expression and rearrange it to solve for the hydronium, and we find that the hydronium concentration equals the equilibrium constant, the acid dissociation constant, really, for the weak acid involved, multiplied by the ratio of concentrations of the weak acid and its conjugate base. So let's see an example of how this works. This problem says the Ka for acetic acid is 1.8 times 10 to the minus 5. What is the pH of a buffer prepared with 1 molar acetic acid and 1 molar acetate ion? And then it gives us the acid dissociation equation for acetic acid donating a proton to water to create the acetate ion and hydronium. This is the same thing we saw in the previous slide. Since we're looking for the pH, what we really need to find is the hydronium, because we know that the equation for pH is that it's the negative logarithm of the concentration of H3O+. So we can either start from the equation on the previous slide at the bottom, if we want to remember that, or we can use the acid dissociation equation and the equilibrium constant equation and solve it from there. I usually do it that way because it's easier for me to remember that. So we would begin with the acid dissociation constant, Ka, which is going to equal the concentrations of the products, acetate and hydronium, multiplied together, divided by the concentrations of the reactants, in this case acetic acid, and we would leave out water again since it's in the liquid state. So this is our expression for the equilibrium constant, or in this case it's really called an acid dissociation constant. And now we just need to solve for hydronium. The hydronium ion concentration is going to be Ka multiplied by the concentration of the acid form divided by the concentration of the conjugate base form. And now we actually have all these numbers. They give us the Ka, it's 1.8 times 10 to the minus 5. The concentration of the acid is 1.0 molar, and the concentration of the base is also 1.0 molar. In this case, these actually cancel out, and you find that the hydronium ion concentration has the same numerical value as the acid dissociation constant, 1.8 times 10 to the minus 5th. However, where the acid dissociation constant has no unit, the hydronium concentration is going to have units of molarity, capital M. If we take the negative logarithm of 1.8 times 10 to the minus 5, we find that the pH equals 4.74. Since there's two significant figures in the coefficient for the concentration, we keep 2 decimal places in the pH. And there's our answer. Since the value of Ka for a particular acid is constant at a given temperature, the hydronium concentration is really determined by the ratio of the concentration of the acid to the concentration of the base. Of course, for a true buffer, this ratio has to be equal or close to 1, and so the hydronium concentration is really going to stay close to the value for Ka. You can add small amounts of acid or base, which will change the ratio slightly, but the hydronium concentration will still stay in a range close to Ka, and therefore maintain an approximately constant pH. Now, you could take this system and add so much acid or base that this ratio becomes very large or very small, but at that point we would say that the capacity has been exceeded and the system is no longer working as a buffer. The general rule of thumb is that a system will behave as a buffer when this particular ratio is less than 10 but greater than 1/10, or 0.1. Buffers can be made from any weak acid-base conjugate pair. Here we have a few examples. First is the acetic acid acetate buffer that we've seen a couple of times. The second is the carbonic acid carbonate buffer system. The third is dihydrogen phosphate and hydrogen phosphate. And the last is the ammonium ammonia buffer system. Each of these examples is a conjugate pair with the acid on the left and the base on the right. Now, because the pH of a buffer depends on the hydronium concentration, and because buffers are designed to keep the hydronium concentration close to the value of Ka for the acid component, the choice of acid-base pair actually restricts the pH range of the buffers we can make from it. We could take the negative logarithm of the Ka to find the exact midpoint of the pH range, but for our purposes it's quicker and easier to just get a rough estimate from the exponent of the Ka value. So for example, the Ka of acetic acid is 1.8 times 10 to the minus 5. This means that we can only use this acid-base conjugate pair to make buffers with a pH close to 5. Don't forget to drop the negative sign in the exponent. For carbonic acid, the power of 10 is negative 7, so we can make buffers close to a neutral pH of 7. In fact, this is the buffer system that exists in your blood and maintains the pH close to 7.4. For dihydrogen phosphate and phosphate, the exponent is negative 8, so the buffer pH must be close to 8. And for ammonium ammonia, it's going to be close to a pH of 10. As you can see, these examples run the range from acidic buffers like acetic acid acetate to neutral buffers like carbonic acid carbonate to basic buffers like these last two. We can use the dihydrogen phosphate hydrogen phosphate buffer system to illustrate how this works in more detail. We saw in the previous slide that the Ka of dihydrogen phosphate is 6.2 times 10 to the negative 8. We start by writing down the acid dissociation equation and the expression for the hydronium concentration. You may be tempted to skip the chemical equation part of this, but in cases like this where both buffer components are actually amphoteric, it's useful to be clear about exactly which dissociation step we're dealing with. That way we can be sure that we're using the correct value for Ka. Remember that the acid is the one with more protons, so in this case, it's dihydrogen phosphate. Now that we have our expression for the hydronium concentration, we can focus on the acid-base ratio. In the case where they're exactly equal, the factor cancels out to 1 and the hydronium concentration equals the value of Ka. Then we can take the negative log of Ka and we find a pH of 7.21. This is what I referred to before as the midpoint of the pH range for this particular acid-base conjugate pair. I also said before that the rule of thumb for a buffer is that the ratio here has to be less than 10 and greater than 1/10. If there's 10 times more acid than base, then the pH will be 1 pH unit lower or more acidic than the midpoint value. If there's 10 times more base than acid, then the pH will be 1 unit higher or more basic. These are the conventional bounds of what we consider a useful buffer solution. By keeping the ratio in that range, we keep the pH in a range of plus or minus 1 unit. If we go any further than that in either direction, we'll be exceeding the buffer capacity and the pH will start to change more rapidly. I mentioned a minute ago that our blood is maintained at a pH of around 7.4 by the carbonic acid bicarbonate buffer system. If our blood pH drops below 6.8 or rises above 8.0, our cells stop functioning properly and the results can be fatal. The carbonic acid in our blood buffer comes from the carbon dioxide dissolved in it. Any CO2 that isn't expired through the lungs remains dissolved in the blood, and some of it turns into carbonic acid through this equilibrium process. This carbonic acid is a weak acid, so it is also in equilibrium with the dissociated bicarbonate and hydronium ions. Dissolved carbon dioxide therefore supplies the acid component of our blood buffer, carbonic acid. The base component, HCO3- or the bicarbonate ion, is also supplied by the kidneys, bringing the concentration closer into balance and forming a true buffer system between the two. In the blood, excess hydronium is neutralized by bicarbonate ions, and excess hydroxide is neutralized by carbonic acid. Together, these processes maintain a pH of approximately 7.4 in our blood. Of course, other factors can disturb these equilibria and cause certain medical disorders. The amount of CO2 dissolved in our blood is determined by the partial pressure of CO2 in the atmosphere that we're breathing, according to Henry's law. If there's too much CO2 in the atmosphere, it will cause more CO2 to dissolve in the blood, which will shift the equilibrium further towards the hydronium side. This lowers the pH and causes a condition known as acidosis. The opposite condition, alkalosis, occurs when the CO2 concentration in the air is too low, leading to an abnormally high pH. That's the end of the chapter on acids and bases, and as usual, this chart summarizes some of the relevant concepts. You may be tested on almost any of these. The only one we don't really get into is the Kb, the base dissociation constant, so you can forget about that one. You won't be tested on that on any of the exams or homework. As far as useful equations and calculations that you would want to practice, you should take a look at the formula for pH. pH equals the negative logarithm of the hydronium concentration, as well as the inverse of this formula, which allows you to calculate the hydronium concentration from the pH, 10 to the negative pH. You'll also want to be able to use the expression for Kw, which allows you to calculate the hydronium concentration from hydroxide and vice versa. And you also want to be able to work with the acid dissociation expression and use that, especially with regards to calculating the pH of a buffer.